Okay. All right, so today we're going to do a bunch of items. So the first thing is going to be some very quick stuff from analysis. Then we're going to move into the Cauchy-Riemann equations. I'm only going to do half of it. It's a nice way of stating when a function is complex differentiable. After that, we will see some applications of this. If you've seen Stokes Theorem, this lecture becomes a lot easier. If you haven't, this becomes a way to motivate why you should go back and learn Stokes Theorem. And then at the end, we'll talk a little bit about differentiating power series. And when is the derivative of a power series the sum of the derivatives? This essentially comes down to interchanging operations. This is what distinguishes us from people in physics. We actually care about rigorous conditions as to when you can differentiate, when you can change the order of operations. If you don't care so much about that, it's a lot easier to do these arguments, but sometimes they fail. Okay, and I'll try to give you an example of a situation where you can't just change the order of integration or the order of differentiation and summation. All right, so we're going to start with complex differentiable. So definition, it's the limit as h goes to 0 of f of z plus h minus f of z over h exists, and we'll call that f prime of z. So right now, there's not that much of a difference between this and what you've seen in standard real analysis. The difference is that this has to hold for all paths. So that's the trick, is all paths. So if we take some strange path like this, we have to get the same answer. In real analysis, we only have two paths. So here's our point. We can either come from it from above, come from it from below. That's it. In complex analysis, the fact that we have to deal with all these paths in some sense makes things harder. You now have to prove that you get the same answer no matter how you go about it. So unfortunately, this does not swivel. Wonderful. We'll try it like this. Or even better, it would be not to swivel since we only have one board. That's one of the advantages of having such a small classroom. So in some sense, we have an issue from complex analysis in that we have to be able to understand this for all possible paths. But if that exists, then we get so much more information. It's a much stronger condition. So let's do some examples. Can somebody give me the easiest possible function to look at? Yes? 0. So can you tweak it just a little bit? 1, or more generally? No, not x. No. I mean, let's not, run before we can walk here. I mean, come on. I mean, this is still, not even 10-10. Instead of, 0 or 1, we could just say, K, are you German? C for constant, okay? So we spell constant with a C in this country, okay? So I'm not going to bother going through this, but what you will see is if you put in f of z as a constant, you'll get 0 for the numerator, and you don't have to worry about the denominator, because it's the limit as h goes to 0 without ever actually being 0. So we never have 0 over 0. We do not like, well, we may like 0 over 0. We're not allowed to work with 0 over 0. All right, this is a little bit too trivial, so now we'll try f of z equals next simplest thing. Z. And we can go through and we'll get the limit as h goes to 0 of z plus h minus z over h. The z's cancel. H over h is 1. Okay, the limit of 1 as h goes to 0 is not so bad. It's just 1. So limit, I'll even be extremely pedantic, is 1. All right, so this isn't so bad. Now, another interesting thing we could do is instead of doing z, we could do z bar. And so z bar is the complex conjugate. So that would be x plus iy with a complex conjugate. A complex conjugate means you replace the I with a minus I. And so we get x minus iy. All right, so now, how does everything change? Well, now, instead of having z, we're now going to have z bar. So we have z plus h bar minus z bar over h. Those of you over 21 should be comfortable with bars. What do we do? The bar of a sum is the sum of the bars. So we can basically just break it up like that. Okay? And again, statements like this you just go through and prove by brute force. If z equals x plus iy and h equals h1 plus ih2, blah, blah, blah. All right, well, if we look at the numerator, there's a lot of simplification. Z bar minus z bar cancels. And we're left with the limit as h goes to 0 of h bar over h. And now we want to evaluate that limit. Now, if you think back to the nightmare over here, if the limit exists, we must show we get the same answer for every single path. If we can find two paths which lead to a different answer, however, we know the limit doesn't exist. So there are two natural paths to think about in all of these problems. What are the two natural paths? Yes?
You can approach 0 from the real axis?
Yes? Or the imaginary axis. Try those two. If those two are the same, you got to do more work. But if those two are different, you're done. So case 1, let's take h is real. And then we would get the limit as h goes to 0 of h over h, because if h is real, the complex conjugate of h is just h. And then that's now the limit as h goes to 0 of 1, and that's 1. Well, the next case is we come down along the imaginary axis. So this would be h is in I times r. And what I'll do is I'll write h as I times k. And if we write it like this way k is real. I am not doing this because I have invested in a chalk company and I want to write as much as possible. You know, if anything, I want to write as little as possible because we only have one blackboard. Why do I want to go through and write h equals ik? Notation matters. Why am I doing this? It's not to fill up class time because I was doing something which I actually had to sign a waiver for last night that I'm not allowed to discuss. And didn't have as much time to prepare this lecture as I wanted. Why am I writing h equals ik? Yes?
It makes the limit more obvious to compute.
Why more obvious?
Because you know the complex conjugate of ik is just minus ik.
Yeah, the advantage of doing this is I can look at it and say k is a real number. I'm used to working with real numbers. I can quickly glance down and see what things are. Remembering that h is an imaginary number. It's the same thing when you're dealing with positives and negatives. I always like to have my constants positive so I can glance down and get a feel for what's going on. If my constant is negative, I'll write it as negative times a positive number. If I don't know if it's positive or negative, well then I can't do anything. But since I have some information, I know it's I times r, it's a pure imaginary number, let's take that into account. So now we get the limit as k goes to 0 and k is real. Now, h bar is the complex conjugate of ik, so it's going to be minus I times k divided by I times k. All right, so this is the limit as k goes to 0. I'm not even going to bother writing k as real, because at this point it doesn't matter, I just have negative 1. And so I get negative 1. So what we've just shown in this case is that unfortunately the function z bar is not complex differentiable. Do you think z bar is real differentiable as a function of two variables? You know, the function that takes x, y and gives you back x comma negative y. Yes, this will be real differentiable, but it will not be complex differentiable. Complex differentiable is a very strong condition. Okay, so the next thing we could do is we could replace z with 3z, 5z, or just more generally c times z. A lot of the old results from calculus will follow exactly as before. If a function's derivative, a multiple of that function is differentiable, and the derivative is the multiple times that. The sum rule still holds, the quotient rule still holds, the product rule still holds, the quotient rule still holds. I'm not going to bother going through that because I actually have more than enough material for the semester. All those arguments follow identically. What's the next function we should look at? Yes? Polynomial, look at z squared and see what happens if you look at z squared. You will find, not surprisingly, the derivative of z squared is 2z. If you go through and you look at z cubed, you'll find the derivative is 3z squared. And you'll then be led to conjecture, I probably believe now that the derivative of z to the n is n times z to the n minus 1, at least if n is an integer. And I'm not going to bother going through all that. It's a good exercise to do. It uses the binomial theorem. The other thing when you're doing calculations like this is it turns out you can do this to try to sniff out relations. So later today we're going to prove the Cauchy-Riemann equations. At some point in your life you might actually be in the situation where you're supposed to remember the Cauchy-Riemann equations. For instance, you might be teaching, complex analysis. And you may not have actually ever remembered or memorized the Cauchy-Riemann equations. But you know roughly what they are. They somehow relate the derivatives of, if I write, f of z as u of xy plus I times v of xy. There's going to be some relations between the partials of u and the partials of v, but I always forget which way they go. If you know one function, if you know the derivative of z squared, you can then correct your guess. And this is an extremely useful technique in mathematics. If you have an approximate formula, if you know a few special cases, you can then correct yourself. Think back to some of the trig identities. If you forget exactly how things go, if you're close, that's often good enough. Okay, so what I want to do now is I want to talk about the Cauchy-Riemann equations. And the reason we want to talk about the Cauchy-Riemann equations is this is not fun. We do not want to explore the derivatives over all possible paths. And so what we want to do is we want to find an equivalent way to determine if something is complex differentiable. So it turns out that there's this one-to-one equivalence. If a function is complex differentiable, then the Cauchy-Riemann equations are satisfied. If the Cauchy-Riemann equations are satisfied, then the function is complex differentiable. I'm only going to prove one direction. The other direction is in the book. All right. So what we're going to do is we're going to write f of z as u of xy plus I v of xy. Well, basically, what I'm saying is I have a function that's supposed to be complex differentiable. Well, if it's complex differentiable, it should be a function of a complex variable z. I can consider z as a function of x and y. It's x plus iy. And no matter what x and y you give me, I get as an output some complex number. I can write that as a real part plus an imaginary part. Let's call the real part u, the imaginary part v. These are letters that are nice and free, they're consecutive, similar to the x and the y. So u and v are going to be functions of the two real variables x and y. So what we're going to do now is we will assume f is differentiable and deduce conditions on u and v. All right? So assume f is, was that someone's phone or? Oh no, that's probably the battery's charging. Okay, good. Assume f is complex differentiable. Find conditions on u and v. So what does it mean for the function to be complex differentiable? It means that this limit exists no matter what path we take. What's a good path to take? Yes, when in doubt, if I ever ask you what is a good path to take, real axis, imaginary axis, think back to Calc 3 when you were doing the partial derivatives. You always go down along the coordinate axes. Why do we want to do something like that? That's going to get us derivatives of u and v in terms of partials of x, partials of y. So the first case is we go along the real axis. So in that case, we're going to write h as just h, which will be a real number. And so we get f prime of z is going to be the limit as h goes to 0 of u of x plus h y plus I v of x plus h y minus u of xy minus I v of xy. It just makes it divided by h. All right, so how do we handle this limit?
Split it up into a real part.
Yeah, split up into the real part and the imaginary part. The limit exists. We'll group the reals together, we'll group the imaginaries together. And we'll get the limit as h goes to 0 of u of x plus h y minus u of xy over h plus I times the limit as h goes to 0 of v of x plus h y minus v of x y over h. And I'm just pulling out I from the limit because I hits both things together. The limit of a multiple is the multiple of the limit. All right, what's this limit now as h goes to 0? Partial u, partial x. So this is going to be du dx plus I dv dx. Or if you want, you can write it u sub x plus I v sub x. This is nice compact notation. The subscript there means I'm taking the derivative with respect to that variable. Okay? So if my function is complex differentiable, here's an expression for it. So we can write over here f prime of z is du dx plus I dv dx. Okay, so this is a good start. Now we do the same thing, except we do it with h going to 0 along the imaginary axis. Okay. I could technically just quickly go through and erase all this, but it's not bad to just do the calculation again slowly. So what we'll do is now we'll say h, so this is now the imaginary axis. H is an I times R, so I'm going to write h as ik. And now we'll get the limit as k goes to 0, and k will be real. It's going to be u of x y plus k minus u of x, plus I u of xy minus, no, I'm doing this wrong, v, right? Now it's going to be minus u of x y minus I v of xy divided by I times k. Oh, and this should probably be a y plus k over here. So x, y plus k. So I'm just evaluating f now at the point x plus I, y plus k. And then I'm subtracting off. So now we do the exact same trick as before. We have the limit as k goes to 0 of u of x, y plus k minus u, minus u of x, y over ik. And now for the others, the imaginary actually cancels with the imaginary down there. And so we get plus the limit as k goes to 0 of v of x, y plus k minus v of xy over k. What's the first limit going to be? Yes?
Minus I times partial with respect to y.
Good, you've got a 1 over I down below. So if you multiply by minus I over minus I, you'll get a minus I squared, which is 1 down below. So this is the same as minus I du dy plus over here, it should be dv dy. And so the whole point is we're just being very careful to make sure that we can interpret these in terms of standard real derivatives. So we can then just write that over here. This is now the same, and I'll write them in the opposite order. dv dx minus I du dy. Could I write the imaginary part first? I could, but it's not going to be as easy to just glance down and see what's going on. We like to always write the real part first. Well, if these two expressions are equal, the only way they can be equal is if the real parts are equal and the imaginary parts are equal. So from this, we can immediately deduce the Cauchy-Riemann equations. And so we now find the following. So going back to the bar metaphor, if this was actually a bar, every time we say either Koshi or Riemann, you would take a shot. And in some sense, you could even see whose name is going to be mentioned the most in this course. It's going to be neck and neck between Koshi and Riemann. These are going to be two of the giants. All right, so we get du dx equals dv dy, and dv dx equals negative du dy. I will now just check my notes to make sure I haven't made a mistake. Ux equals vy, good. Uy equals negative. Okay, sometimes they actually like to migrate the minus sign over to here. Doesn't make much of a difference where you put the minus sign. So it turns out the Cauchy-Riemann equations hold if and only if f is complex differentiable. So we showed one direction. The other direction is in the book, and it basically goes through by saying if the limit exists, you can write it basically as this linear approximation plus something that's going to 0 extremely fast. And then you just go through and you see that this implies that it's complex differentiable. This is very similar to what should have been done in Calc 3. Whether or not it was done in Calc 3, I don't know. But if you really wanted to decide what does it mean for a function to be differentiable as a function of several variables, it's not enough for the partials to exist. And that's where some of the subtlety is coming from. So the Cauchy-Riemann equations are often important. If you forget what they are, just take the function z squared and calculate the partial of u, the partial with respect to x and y, the partial of v with respect to x and y. You know there's got to be some relations going back and forth. And there's got to be a minus sign somewhere. If you just go through and work with z squared, you'll figure out which way things go. Okay, so these are the Cauchy-Riemann equations. Any questions on what we've done up till now? Yes?
Can you write any function f of z as u plus iv?
Absolutely. Whether or not u and v are nice functions is a completely separate story. I can always say, call u the real part, call v the imaginary part. Just because I write it down does not mean I can work with it. If the function turns out to be complex differentiable, then the hope is that maybe u and v will be nice functions. And in fact, u and v have to be somewhat related functions. We've got these equations here. So here's an interesting question to ponder. You should always be thinking about questions you can ask. So I will start the semester off by giving you one to think about. I'm thinking of a complex differentiable function, and I will tell you u. Do you know v? Is this enough information to figure out what v is? What do you think?
No, for one you get a constant.
Good. So first of all, I can always just tweak v by adding, 2015, 24601, 1701, 1793. I can always tweak v by adding a constant. And just by knowing u that I'm not going to be able to determine things up to a constant. So I could either say, fine, up to a constant, or I give you u and I give you the value of f of 0. I give you the value of f at one point. Is that enough to uniquely determine v? I now have a system of differential equations. I know how v changes with respect to x. I know how v changes with respect to y. So if I give you a complex differentiable function, do I really need to give you v? If I just give you the function in one point? Or can you now deduce this? So you should be able to deduce v from this information. Okay. Other questions about the Cauchy-Riemann equations? But I mean, this is a really nice consequence. That, in some sense, if I run out of chalk and I stop over here, you're fine. You can fill it in. It may be a lot of work for you to fill it in, but you can fill it in. Okay. So the next part is moving to Stokes theorem or Green's theorem. Sometimes they call it Stokes theorem in the plane. How many of you have seen Stokes theorem or Green's theorem? How many of you can still state Green's theorem? I mean, in all fairness, I did have to prepare this lecture. How many of you can prove Green's theorem right now if you had to? Okay, so it turns out complex analysis is essentially equivalent to Green's theorem. The main difference is we don't necessarily apply it to functions that are well defined. We apply it to functions that blow up, and we exploit the blow-ups. So what I want to do is I want to talk a little bit about Green's theorem, and then use this to motivate the big result in the class, Cauchy's residue theorem. It'll be a while before we prove Cauchy's residue theorem, but this will give you some sense of why it's true, and it will give you some power of the Cauchy-Riemann equations. One of the things I often hate in classes is when you just prove results almost for the sake of proving results. And the question is, why do we care about the Cauchy-Riemann equations? Well, one is, if I only know the real part of my function, the Cauchy-Riemann equations allow me to recover the imaginary part. Already, that should be enough motivation that you should be thankful that, hey, this was a good lecture after all. You know, showing up today was a good idea. For those of you who are taking the class remotely, I apologize. Another application of this is that we can now get some sense of the big result of the class, the Cauchy-Riemann equations. So Green's theorem. And maybe next time I'll bring one of my props on Green's theorem. Omega is a nice closed region. D omega is the boundary. Let's say no holes, and everything is nice. All right? Think circle, rectangle, stuff like that. Okay? If I give you a function, a vector-valued function, I'll write this as p of xy, comma, q of xy. I'll sometimes put an arrow over things just to remind you it's vector valued. A lot of what I'm doing right now is motivation. If you haven't done this in Calc 3, don't worry. I just want you to have some sense of where everything is coming from. Then if I look at the integral of f dot ds, and does anybody know why I put a circle around here? It means it's closed. So I want a closed boundary curve. Okay? So if I look at this closed integral, this is going to turn out to be the integral over the boundary of omega of p dx plus q dy. It turns out this is the same as the integral over all of omega of dq dx minus dp dy dx dy. So this is Green's theorem. If I had multicolored chalk, obviously you can figure out what I would do here. Okay? Incredibly useful result. It says I can convert a line integral to an area integral, or an area integral to a line integral. Which would you rather evaluate, a one-dimensional integral or a two-dimensional integral? Yes? It depends. What functions do you think we love to apply Green's theorem to?
One-dimensional
No.
line integrals?
Well, that's what's going on. What kind of relation do you want Q and P to have?
They're equal.
I'm sorry?
They're, I don't know, they're equal at the end.
Well, if P and Q are equal, it's not quite P and Q being
Or
equal.
partial-
Yes,
partial.
you want dq dx to equal dp dy. Okay? So if dq dx equals dp dy, then life is good. Now, this is also extremely highly trivial. And you might be a little bit concerned about creating an entire upper-level graduate class based on the fact that we're going to be integrating 0. So it turns out what we're going to do is we're going to tweak these integrals just a little bit. But essentially it comes down to integrating 0. Integrating 0 is not that hard. I don't really care what I'm integrating over. I can integrate 0. Okay? That's why Green's theorem is so useful. Anybody remember what this quantity is called? Yes. This is called the curl. And so what you can really do is you can view this, if you want, as this is a 3-dimensional vector. There's p of xy, q of xy, and then there's a third component that's identically 0. What's going on here is you actually have a dot product, and you have a 3-dimensional. I'm not going to go into all of this stuff. I don't really want to find out how much people remember from Calc 3. But if you do remember that stuff, there's an interpretation of what's going on, and that allows you to go from Green's theorem in the plane to Stokes' theorem in greater generality, to integrating over surfaces in 3 space. And so the idea is that this line integral is often useful. In physics, it's often the work being done on a force as you move, a particle along a given path. So this is a quantity you might actually want to compute. In other words, there's a reason why we're learning how to do integrals. Okay. Does anybody remember a proof of Green's theorem? I will quickly sketch a proof. I don't want to go into too much detail, but proof sketch. So the reason I want to sketch the proof is it allows me to highlight a really good idea. You want to break up a complicated problem into simpler problems. So if I give you a general region, I want to break the region up into a lot of smaller regions where the problem is easier. What kind of region is the simplest to break things up into? Yes?
Sorry, could this be a curved surface?
Yeah, of course. So I could have something like this.
But like bend?
No, because we're in 2 dimensions.
My hand. Okay.
We're in 2 dimensions.
So little discs.
Little disks. The problem with little disks is the little disks will not fit together perfectly.
True. Little rectangles.
Little rectangles. What else? There's one other shape that's competing with rectangles. Well, squares are just special rectangles. And the problem with squares is that forces all the sides to be equal, and that could be very restrictive. Triangles. So I know Professors Garrity and Adams have lots and lots of fights. And we can discuss later what actually happened to Professor Garrity's foot. But if we want to think about what's going on, if we want to break up a complicated region, do we want to break it up into triangles, which only have 3 sides, or rectangles, which have 4? Which would you rather do? Good, I was able to successfully lead you. No, we want squares and rectangles. So the thing is, triangles are really nice. I can keep fitting them together. I can triangulate a region without any trouble. But if you look at the integral I'm doing here, I'm integrating p dx plus q dy. This is telling me I want things that are parallel to the x and y axis. So even though the rectangle has one more side, things align much nicer. And so the idea, and I'll only do it partially, is I split my region into lots of smaller subregions. And I prove Green's theorem in each of these regions, and then I expand from the interior to the boundary. So I'm not going to go through all the stuff that goes on as you pass from very close to the boundary to the boundary. Roughly, there's a couple of things you could do. One idea is if I want to look at the line integral f dot ds, is I can do a polygonal approximation to the boundary. And if I replace the boundary with a polygonal curve that's segments parallel to the x and y axis, that's not going to really change the integration here that much. It's not going to change the area integration that much. So I can assume my boundary curve is polygonal, and then I can break things up perfectly into pieces. Otherwise, I'm going to have to deal with very small things. And so what I'm going to do is I will just look at what's going on, say, inside. So when you do these integrations, you always integrate counterclockwise. Okay? So whenever we do line integrals, we always choose the counterclockwise normalization. Does it matter which way you integrate? Up to a negative sign, but could we have developed the whole theory doing clockwise integration?
Yes.
Yes. And our answer would be different than all the other books. We have enough problems with the mathematicians and the physicists using different normalizations. If you prove the Riemann hypothesis, and you insist that you will publish your proof only if everybody switches to clockwise integration, you'll succeed. Barring something like that, there is so much tradition now of integrating counterclockwise. This is how we integrate. So if you look at what's going on in the integration here, we now have, in this integral, we go this way, this way, this way, this way. On this segment, and what do you notice? These cancel. When you look at this next one over here, what you'll see is all the interior pieces cancel in pairs. And so if you can prove Green's theorem for a rectangle, all the internal pieces cancel out and it pushes out to the boundary. So you only have to prove Green's theorem for a rectangle. And now you just do the integration directly. When you look at dq dx, how would we do that? So I want to integrate over omega dq dx dx dy. I can integrate with respect to x first and then with respect to y, or with respect to y first and then with respect to x. Which should I integrate first? Which is the easy integral to do? Take the derivative of q with respect to x and then integrate with respect to x, or take the derivative of q with respect to x and then integrate with respect to y. So we do this one x first. For the other one, the integral over omega dp dy, which order do we want to do it? The other way. We would do that one dy dx. So we're using a little bit of Fubini here to say we can switch the orders of integration, or to just say we have a choice of what's going on here. If we now do this, we'll get a q, and we'll evaluate q at the endpoints. And then we'll have an integral of q dy that's exactly this piece. And here, the minus sign is going to be because we're now integrating things in the opposite order of what we want. I'm not going to go through and do all the details. It's a great exercise for you to do. I'll post a link which goes through and proves this in a day. But this is essentially why Green's is true. And you can see from looking at this proof what's happening. Okay, any questions on the Blitzkrieg introduction to Green's theorem? So we have some idea of why it's true. We have some idea that it's nice to break things up in terms of squares or rectangles. And this is going to be a big fight throughout the semester. Do we want to do things in terms of triangles? Do we want to do things in terms of squares and rectangles? If you actually have to do a calculation, the squares and rectangles are better. If you're just doing things with theoretical nonsense, triangles are much better. Okay. So that was the proof sketch. So now, why do we care about this? So applications, too complex. So we have f of z is u plus iv. And dz will be dx plus I dy. And again, this is really u of xy plus I v of xy. But we're going to just abbreviate things and not bother writing this out all the time. All right, so now let's integrate over the boundary of some curve of f dz. I promise I will prove things rigorously later in the semester. Right now, let's just play fast and loose with the mathematics and see what happens. One of my favorite moments freshman year is I was taking an advanced physics course, and my professor said, in your math class, they'll spend 6 weeks justifying the following step. Moving on, we see. So we will come back, but let's just play. All right, so we're integrating over the boundary of omega of u plus iv, and then dz becomes dx plus I dy. So now I get the integral over the boundary of omega. I'll have a u dx, and then a minus, an I times an I is a minus I, so minus a v dy, plus an integral over the boundary of omega. And I can pull out the I, and I'll have a v dx plus a u dy. What should I do now? So what should I do? How should I try to evaluate these line integrals?
If you could
Yeah, Green's theorem. I mean, one of the advantages of there's not much left on the board, there's not much board space. I can't keep things on the board that are fluff. Anything on the board is extremely important. Green's theorem was not erased. Let's use Green's theorem. So in this case, P is equal to U and Q is equal to negative V. So now I'll get dq dx minus dp dy. I can factor out the negative sign. I'll get integral over omega. I'll get dv dx plus du dy plus I. And now when I do the integral of omega here, my q is equal to u, so I'll get du dx minus dv dy. What does this integral equal? There's only one thing it can be if I'm asking you what does it equal.
0.
It's got to be 0. Why does this integral equal 0? It's the Cauchy-Riemann equations. The Cauchy-Riemann equations say du dy is negative dv dx. So this is now the Cauchy-Riemann equations. What does this integral equal? 0, because of the same thing, Cauchy-Riemann equations. So here is a quick proof that if you have a function which is complex differentiable, its integral along a nice smooth curve is going to be 0. What we will then do is we will then tweak our function. We'll have our function blow up at a finite number of points. And then what we'll get is we'll get 0 plus a very nice computable part. Okay? So this is trying to motivate why complex analysis is going to work. This is trying to give you a sense of what's coming. How many of you, this is a dangerous question to ask because in Math 150, anybody here take Math 150? Okay. So did you see green at all?
Not really.
Okay. So in 150 you won't see green. In 151 you'll see green, but maybe you won't actually do any calculations with it. So what you'll often have is you'll have some region like this, and your function will blow up at a couple of points. And so the way it works is what you do is you take very small circles about these points. And you initially travel your curve like this. What happens is now you come down here, go around the curve, and then come back. Same thing here. Same thing here. So these internal segments all cancel. And now what you have is you have a nice region on the outside of these 3 points where you can apply Green's theorem, and the integral will be 0. And you reduce the integral over the initial curve with the 3 bad points to the sum of 3 integrals of circles centered at the points that blow up. So the whole idea is we reduce every integral we need to do to integrating a function over a very small circle. And it turns out that a function that blows up, we can actually analyze it perfectly in terms of these integrals. Circles are nice. If we want to break it up into lots of circles, no. But if we want to just do an integral, integrating over a circle is very nice. So this gives you some foreshadowing of what's going to happen. Okay, any questions in terms of what we've done so far? We've got about 5 minutes left if that clock is accurate. No, 6 minutes left. Okay. So rather than starting to go into some of the analysis in the 3 epsilons, I think what I'm going to do is I'm going to move that to Wednesday's class, and I'm going to try to integrate over circles. Hopefully this has now motivated you that this is worth integrating. So let's do some basic integration. So what I want to do is I want to integrate over the boundary of the disk centered at 0 of radius r of z to the n dz. And so if I have a disk of radius r, I can write z as r e to the I theta, and dz, well, since I'm on a disk of radius r is not changing, and I will just get I r e to the I theta d theta. And so my integral becomes the integral theta goes from 0 to 2 pi of z to the n becomes r to the n e to the I n theta times dz, which is I r e to the I theta d theta. Well, we now collect terms. I can pull out the I can pull out an r to the n plus 1, and I have the integral theta goes from 0 to 2 pi of e to the I n plus 1 of theta d theta. You will find that I like to do extra notation. There's a lot of quantities in this problem. I like to put the theta as a subscript on the integration so I know what's my quantity that's moving. So I want to evaluate this integral. Now, in some sense, this might be a little bit of an unfair integral to do. This is complex analysis, and we haven't really done complex integration. I can write this, if I want, as a sine and a cosine. So this is I r to the n plus 1 integral theta goes from 0 to 2 pi. And I'll have cosine n plus 1 theta plus I sine n plus 1 theta d theta. All right, it's time to use that prereq material. What is the integral of cosine of some integer theta over a complete period? Is it always 0? What's the one danger? If n is negative 1, I'm integrating cosine of 0. Cosine of 0 is identically 1, and then I would get 2 pi. Otherwise, I get 0. For sine, I don't even have to worry about that. And so this gives us the following. The integral over the boundary of the disk of radius r of z to the n dz is equal to 2 pi I if n equals negative 1 and 0 otherwise. Well, this suggests that I should consider these integrals and divide by 2 pi I, because then I can just write it as 1. So if I integrate 1 over 2 pi I z to the n dz over a disk of radius r about that point, I get 1 if n equals negative 1 and 0 otherwise. Yes?
What about the r to the n plus 1?
Ah! What's the only value of n I need to worry about?
Oh,
I really need to only worry about every now and then life works out. Earlier somebody, I won't mention who, kicked the tripod just a little bit, and so I can't quite swivel back anymore. But all right, so we have this beautiful formula. If I now want to integrate, say, along some closed curve, f of z dz, the idea is I write f as a series expansion. And what I'll get is I'll get a sum over all zk such that f of zk has a pole. And then I'll get 1 over, I'll put a 1 over 2 pi I over here. And then what I'll get is I'll have the integral 1 over 2 pi I over the boundary of the curve. And what my curve will be the disk centered at the point zk of, say, radius epsilon. And then I'll have a sum, n goes from minus infinity to infinity, of a sub n z minus zk to the n dz. So this is the main thing we're going for. I take my function and I expand it about all points where it blows up. The integral of a sum is going to be the sum of the integrals. The only term that will survive is when n equals -1. And we'll just get a sum of how much the function is blowing up at those points. And this is how we can now deduce any integration from just knowing the integration over a circle of a function that blows up and then having this application of the Cauchy-Riemann equations, the Stokes theorem. Okay, so in Wednesday's class, we will do more in detail on 3 epsilons and some results from analysis and talking about when you can differentiate a series and what that will be.